Welcome back to Basic Electronics. In the last lecture, we showed that correct biasing of the BJT is crucial in amplification. We also looked at a simple scheme to establish some given bias condition. But this scheme was found to be very sensitive to the beta of the transistor, and therefore it is not used in practice. We will now look at an improved biasing scheme and show that it is much more robust with respect to variations in the transistor beta. We then turn our attention to the second major issue in BJT amplifiers, that is adding the signal voltage to the bias voltage. We will illustrate how a coupling capacitor can be used for this purpose. So let us get started. Here is an improved circuit, and we will see that the dependence of IC or PCE on the transistor beta in this circuit is much weaker than the previous circuit. To analyze this circuit, let us redraw. So what we have done here is instead of showing VCC like that, we have drawn that explicitly, and let's check that the circuit is still the same as before. From the base we have R1 going to VCC. Here from the base we have R1 going to VCC. This node is the common node or ground shown here. From the collector we have RC going to VCC. Same thing here, collector, RC, and then VCC. So these two circuits are actually the same. Now what we will do is to look at this part and find the Thevenin equivalent circuit. What is the Thevenin resistance? Let's deactivate this independent voltage source, and then we see R1 and R2 in parallel, so that is RTH. What about VTH? The open circuit voltage here. So imagine that nothing is connected here, and then this voltage is R2 divided by R1 plus R2 times VCC. So that is our VTH. So after making that transformation, we get this circuit. Let us calculate VTH and RTH. VTH is R2 by R1 plus R2 times VCC. R2 is 2.2K, R1 is 10K. So VTH is 2.2 by 10 plus 2.2 times 10 volts, and that turns out to be 1.8 volts. What about R Thevenin? R Thevenin is R1 parallel R2, so 10K parallel 2.2K, and that comes to 1.8K. And now we know everything about this circuit here, and let us now write the Kvl equation for this loop, assuming that the BJT is in the active mode. So what does Kvl say? Kvl says that this voltage drop VTH is the sum of three voltage drops, RTH times IB, the first term here, VBE about 0.7 volts, the second term here, and RE times IE, the third term here. Now IE is beta plus 1 times IB, and therefore we can write KVL as VTH equal to RTH times IB plus VBE plus beta plus 1 IB times RE. Alright, we can now solve this equation for IB, and we get IB equal to VTH minus VBE divided by RTH plus beta plus 1 times RE. Now I see the collector current in the active mode is simply IB times beta, and therefore we get this expression for IC. All we need to do is simply multiply this expression here by beta. Now let us calculate the collector current for beta equal to 100 first, and that turns out to be 1.07 milliamperes. If we increase beta to another value, let's say 200, then IC turns out to be 1.085 milliamperes. And we notice that there is hardly any difference between these two numbers. For all practical purposes, they are the same. And this of course is a big improvement over the previous circuit, in which IC was very sensitive to the value of beta. Here we have changed beta by a factor of 2 and see hardly any difference in the collector current value. So this is a big advantage of this configuration, and it is therefore commonly used for amplification. Having obtained IC equal to 1.1 milliamp, let us now proceed and get the other quantities of interest. What about VE? VE is IE times RE, and IE is nearly equal to IC because our beta is large enough, about 100, and if beta is 100, then alpha is beta divided by beta plus 1, or 100 divided by 101. That's very close to 1, and therefore we can say that IC and IE are nearly the same. So we will use for IE 1.1 milliampere, so that times 1K is 1.1 volt, and that is what is indicated over here. What about VB? VB is VE plus this voltage drop, which is 0.7, so 1.1 plus 0.7, 1.8 volts. What about VC? VC is VCC minus IC RC. VCC is 10, IC is 1.1 milliamp, RC is 3.6 K, so that turns out to be 6 volts. And now we see immediately that the BJT is actually operating in the active mode. NPN, P is at 1.8 volts, N is at 6 volts, so N is higher than P, therefore the base collector junction is under reverse bias. So that tells us that the BJT is operating in active mode or linear region. What about this voltage difference? VCE 6 volts minus 1.1, so that turns out to be 4.9 volts. There is a way to quickly estimate the bias values if we assume that beta is very large, say infinite. And what is the implication of a large beta? The base current IB is IC over beta, and if beta is large, then the base current is small. So what we're going to do is ignore the base current, which is fair if beta is large, and in that case this current is 0, negligibly small, and therefore this 10 volts gets divided between R1 and R2. This is like an open circuit, so there is no current there, and then we can obtain VB simply by voltage division, R2 by R1 plus R2, R2 by R1 plus R2 times VCC. So that turns out to be 1.8 volts. Once we get VB, we know that the base emitter junction is under forward bias, so there is a voltage drop of 0.7 volts there, so 1.8 minus 0.7, that is 1.1 volts. IE, once we get VE, IE is simply VE divided by RE, or 1.1 milliamp, and if beta is large, then alpha is equal to 1, and IC and IE are then equal. So IC is alpha times IE, nearly equal to IE, that is 1.1 milliamp. And then we can quickly find VCE, VCC minus IC RC minus IE RE. VCC minus this voltage drop minus this voltage drop, that is VCE. So that is 10 minus 3.6 K times 1.1 milliamp, that is ICRC, minus 1K times 1.1 milliamp, that is IERE, and that turns out to be 5 volts. So there is a slight difference here. The earlier VCE was 4.9 when we actually considered the value of beta about 100, and if we consider beta to be very large, then it is 5 volts. So 4.9 there and 5 here, not a big difference, and very often this quick estimate of the bias values is very helpful. Okay, we have now found a reasonably good biasing scheme which is insensitive to the transistor beta value. And now the next challenge is to add the signal to the bias. So here in this circuit there is no signal anywhere, there are only DC quantities or bias quantities. Now to that we want to add the signal. If we cannot add the signal, of course the whole amplifier is useless, because then it will not be amplified. So the input signal Vs of t, which is typically taken as a sinusoid, for example, needs to be mixed with the desired bias value Vb, so that the net voltage at the base, this voltage, is the DC component, which we have already computed in the last slide, and in that example it was 1.8 volts, plus the signal. Now the signal we have taken as a sinusoid, but in general it need not be a sinusoid. For example, if we have an audio application, then it's not one signal frequency, but a whole bunch of frequencies with different Fourier components and so on. So if you look at the audio signal in time domain, it will look very different from a pure sinusoid. But for simplicity of analysis, we often take V cap sine omega t as the input signal. So let's proceed with that. So now the challenge is to mix these two, and this can be done by using a coupling capacitor Cb, the coupling capacitor there. So we have the signal here, V cap sine omega t, for example, and we have the rest of the amplifier, and we connect the signal to the rest of the amplifier with this coupling capacitor. It's called coupling capacitor because it couples the signal to the amplifier. And how does it work? So let us explain that by considering a simple circuit that will illustrate this idea of a coupling capacitor. Okay, let's start with this simple RC circuit. Let's leave the BJT aside for the moment, because it makes life more complicated. And for this RC circuit, we have two sources. One is a DC source, V0, and one is a sinusoidal source, Vm sine omega t. And we are interested in the solution. What do we mean by the solution? Currents and voltages in the circuit in the sinusoidal steady state, and we have come across this term earlier. What is sinusoidal steady state? That is when the exponential transients have vanished, and the exponential transients arise because we have a time constant in this circuit. So there will be things like e raised to minus t by tau, and if t is sufficiently large, then those terms would go to 0, and that is what we mean by the exponential transients have vanished. So after that has happened, each quantity x of t, could be a voltage, it could be this voltage, it could be this current, is of the form a constant x0 plus a sinusoid, and the sinusoid has an amplitude of xm and a phase of alpha. Our job now is to find x0 and xm and alpha. That means the complete solution for x of t in the sinusoidal steady state. There are two ways of going about it. One, solve the circuit equations directly. Let us see how to do that. Let's say that this node voltage is V sub A, and this is the total voltage, that is, it has a constant part as well as a sinusoidal part. Now this current here is VA by R1, and now we are talking about the instantaneous current, VA divided by R1, that current there. This current is VA minus V0 divided by R2, because this node voltage is with respect to this ground, V0. So VA minus V0 divided by R2, that is this second term here, and this current plus that current must be equal to the current entering this node from the capacitor side. And what is that current given by? It is given by C dVc dt. What is Vc? Vc is Vs with respect to this ground, Vs minus Va. So C d dt of Vs minus Va. So that is the equation that we get. That's one way of doing it. And of course we can imagine that it's not easy to solve this equation. So therefore there is a second way which we might find much easier, and that is to use the DC circuit plus AC circuit approach. And we will see what this is in the next slides. What we are now going to do is to consider these components one by one and see how they behave when a combination of DC and a sinusoid is applied. So let's start with a resistor. We have VR, the voltage, equal to a constant part, and a sinusoid, VR cap sine omega t plus alpha. And here is a new notation that we have introduced. Small v, capital R, is the total instantaneous voltage. Capital V, capital R, is the DC part, and small v, small r, is the sinusoidally varying part, that is given by VR cap sine omega t plus alpha. Similarly, we have the current given by a constant plus a sinusoidally varying part, and we are considering the sinusoidal steady state in a circuit, and this resistor is a part of that circuit. And we know that for a resistor, the total instantaneous voltage is simply R times the total instantaneous current. And when we substitute for PR and IR, we get this relationship. And we can split this into two equations. One, capital V, capital R is R times IR, this part, and small v, small r is R times small I, small r. These are the DC quantities VR and IR, and these are the sinusoidally varying quantities. In other words, we can think of a resistor in this situation where there is a DC and sinusoidal part to be described by two circuits, a DC circuit and an AC circuit. In the DC circuit, we have the DC quantities, capital V, capital R, and capital I, capital R. They are related by this equation, which is the resistor equation. Then we have the AC circuit, in which we have small v, small r, the sinusoidally varying part, and small I, small r, again the sinusoidally varying current, and they are also related by the same behavioral equation. So small v, small r is R times small I, small r. So in the DC circuit as well as in the AC circuit, the resistor essentially looks the same. It behaves like a resistor, and the relationship is V equal to R times I, where V and I could be either the DC quantities or they could be the sinusoidally varying quantities. Let us repeat it for the capacitor now. So we have again a total instantaneous voltage, a DC part and a sinusoidal part, total instantaneous current, a DC part and a sinusoidal part. So these are constants and these vary sinusoidally, and because the capacitor involves a derivative, we have made these alpha and beta different, and at this stage we don't know what the relationship between alpha and beta is, but we'll find out. Now, since the total instantaneous current is C d dt of the total instantaneous voltage, we substitute for IC like that and for VC like that, and now we can once again split this equation into two. The first one relating the DC quantities, IC is equal to C d dt VC, and that is 0 because VC is a constant. The second equation, this small I small c is c d dt of small v small c. That is the second equation, and this equation looks pretty much like a capacitor equation. And what does this correspond to? This is saying that the DC current is 0. So that means in the DC situation, the capacitor is an open circuit, not surprising. And in the AC situation or the sinusoidal situation, we have the same equation as we would have for the total instantaneous quantities. So the capacitor in this situation, in the AC situation, looks like a capacitor. And can we now figure out what is the relationship between alpha and beta? We can turn this into a phasor. We can turn that into a phasor and then go through the phasor analysis. And then we will see that the current leads the voltage, and therefore they are related by beta equal to alpha plus pi by 2. What about a DC voltage source? The equation is the total instantaneous voltage is a constant, and because it's a constant, there is no sinusoidally varying part, that is 0. And so in the DC circuit, we have that constant voltage source, and in the AC circuit, we have voltage equal to 0, that is a short circuit. And the DC current, capital I sub capital S, is shown in the DC circuit, and the sinusoidal current or the AC current is shown in the AC circuit, that is small I sub small s. Let's look at an AC voltage source. The equation is the total instantaneous voltage is 0 DC plus the sinusoidal part, the time varying sinusoid. Now, since the DC part is 0, the DC circuit simply has Vs equal to 0, which is a short circuit, and the sinusoid is then incorporated in the AC part. So the AC circuit is simply a voltage source, an AC source, and the DC circuit is a short circuit. Once again, the DC current is shown in the DC circuit, capital I sub capital S, and the AC or the sinusoidal current is shown in the AC circuit, small I sub small s. We can now use the findings in our original RC circuit. So we replace R2 with its DC equivalent, which is also a resistor, and the AC equivalent, that's also a resistor. Similarly for R1. What about the capacitor? The capacitor, as we have seen in the DC circuit, it's an open circuit, and in the AC circuit it looks like a capacitor. The DC source in the DC circuit is a DC source, and in the AC circuit is a short circuit, 0 volts. Similarly, the AC source is a short circuit in the DC circuit, and in the AC circuit it is the sinusoidal source. So we have split the original circuit into a DC circuit and an AC circuit, and we know how to get these from the original circuit by systematically replacing each of the components. Now let us write equations for these two circuits, the DC and the AC circuits. For the DC circuit, we have VA over R1, this VA over R1, that current, plus VA minus V0 by R2, VA minus V0 by R2, that current, and they should add up to 0 because this is an open circuit. Remember, capital V sub capital A is a constant voltage. For the AC circuit, we have small v sub small a divided by R1, that current, plus this current, which is small v small a divided by R2. So that is the sum of those two currents, that current and that current. And let's remember that this quantity is a sinusoidally varying quantity and it has no constant in it. Now these two currents, the addition of these two must be equal to the capacitor current, and that is given by C d dt Vs minus Va. So that is the equation we get for the AC circuit. If we add equations 1 and 2, we end up with equation 3 here. And what is it saying? It is saying that the DC VA plus the AC VA divided by R1, that is the total instantaneous current, plus the DC VA plus AC VA minus V0 divided by R2, that is the total instantaneous current through R2, should be equal to C d dt Vs minus Va, and both of these are sinusoidal quantities. Let's compare this equation with what we had obtained earlier directly from the original circuit, and that equation is here. This is the total instantaneous quantity. This is also the total instantaneous quantity. This is instantaneous Va minus V0. This is also the instantaneous Va minus V0. And what about this capacitor current? D dt Vs minus the instantaneous Va. Now this instantaneous Va has two parts. One is the constant part and one is the sinusoidal part. And the derivative of the constant part, of course, is 0, and therefore we get the same term as this one here. So in other words, equation 3 and 4 are actually the same. And this is a very powerful statement, because now instead of computing Va directly from equation 4, we can compute the constant part using equation 1, the sinusoidal part using equation 2, and then use the instantaneous Va as the sum of DC Va and the AC Va. We can do this computation separately, and that's a big advantage, and then just simply add them to get the total quantity. So this is a very useful approach, splitting the original circuit into a DC part and an AC part, working on the DC circuit and the AC circuit separately. It turns out to be much simpler than working on the original circuit, and then simply adding the two solutions to get the total instantaneous quantities. To summarize, we looked at a robust BJT biasing scheme and showed that it is relatively insensitive to the beta of the transistor. We then discussed the use of a coupling capacitor to couple the signal voltage to the amplifier. We have considered an RC circuit to explain how a coupling capacitor works. In the next class, we will consider a BJT amplifier with a coupling capacitor. So see you next time.